I'm going to go through this example problem where we determine the liquid mole fraction of a binary mixture in vapor-liquid equilibrium. The problem statement says we have a mixture of toluene and polystyrene that's placed in an evacuated closed container. The container is brought to 20.57 bar and 301 degrees Celsius, where the liquid solution is in equilibrium with pure toluene vapor. Because polystyrene is large, you can assume that no polystyrene is in the vapor phase. Calculate the mole fraction of the toluene in the liquid. You may neglect the Poynting correction, and they give us a plot of the activity coefficient of toluene in polystyrene. So basically what we have is a closed container with a liquid comprised of species 1 and 2 in vapor-liquid equilibrium with a pure vapor of species 1 at a pressure of 20.57 bar and temperature of 574 K. The first thing to do in solving this problem is to set up the vapor-liquid equilibrium equation, which says that the liquid fugacity of a mixture of component I is equal to the fugacity of the same component in the mixture in the vapor phase. Let's apply this to toluene because toluene is the only species that's present in both the vapor and the liquid phase. From here, we know that toluene is the only species present in the vapor phase, so y1 is going to be equal to 1. And since it's pure toluene vapor, this fugacity coefficient is going to be the fugacity coefficient of a pure species. We know the pressure of the system, and from the plot we can find what x1 and gamma 1 would be. So what we need to do to solve the problem is to solve for this fugacity coefficient and the liquid phase fugacity. Since the pressure is so high, we know that the system is not going to behave ideally, and we're going to need to choose an equation of state to account for the non-ideality when calculating the fugacity coefficient and the liquid fugacity. For simplification, I'm going to choose the van der Waals equation of state because in the textbook there is already a derivation for the vapor phase fugacity coefficient of a pure species according to the van der Waals equation of state, and it's found in example 7.2 in the textbook. In example 7.2 in the textbook, they show the derivation that the fugacity coefficient of pure vapor species using the van der Waals equation of state is this expression right here. But if you were choosing to use any other equation of state, you would use this equation right here in order to get the fugacity of species I in the pure vapor phase, and then you would use this to get the fugacity coefficient. From the back of the book, you can find that for toluene, the critical pressure is 41.14 bar, and the critical temperature is 591.7 Kelvin. Using these numbers, you can calculate the van der Waals constants A and B, and you'll find that A is equal to 2.48 and B is equal to 1.495 times 10 to the negative fourth. Plugging in all the numbers to the equation we had from example 7.2, we'll get that the fugacity coefficient of the vapor phase is equal to 0.852. Now we need to calculate the fugacity of toluene in the liquid phase. This is the equation we're going to use to calculate it because this third term right here, which isn't written in, but is the Poynting correction factor, they said in the problem statement that it was negligible for this situation. We can calculate the saturation pressure of toluene using the Antoine's equation in the back of the book. Using that, we find that the saturation pressure of toluene is 31.26 bar at 574 Kelvin. Now, to calculate phi I sat, all that we're going to do is use the same expression that we had from example 7.2, except we're going to plug in all the same numbers, except this P right here is now going to be the saturation pressure instead of the regular pressure of the system. Doing that, we get that phi I sat is equal to 0.785, and then plugging the numbers that we found into the expression for the fugacity of toluene in the liquid phase, we get that it is 24.54 bar. Going back to the vapor-liquid equilibrium equation we had earlier, we now have everything that we need to solve for the product of x1 gamma 1. Doing that, we find that the product of x1 gamma 1 is 0.714. And from here, to solve for x1, all we need to do is go back to the plot that we were given and try to find a point on this line to where x1 times gamma 1 is going to be equal to 0.714. Looking at the line and approximating some of the calculations, we'll find that at x1 equals around 0.68 is when the product of x1 and gamma 1 is around 0.714. This gives us our final answer to the problem, that the mole fraction of toluene in the liquid phase is around 0.68. I hope you learned something from this video and that it helped you understand how to solve the problem. If you like this video, give it a thumbs up and subscribe, and we'll be posting weekly videos for Chemi 211 at Purdue University.